for
chemistry.
Yeah, baby.
Welcome to the AS Chemistry, Paper 1, Inorganic and Physical Chemistry, 18th of May 2020. And let's get to the marks. Don't forget to subscribe, like the channel, have a go at the actual paper first, and then check out this walkthrough for the explanations. If you like, subscribe. Okay, question 1. This question is about atomic structure. 1.1, there is a general trend for an increase in ionization energy across period 3. Give one example of an element that deviates from this trend. Explain why this deviation occurs. 3 marks. You get 1 for naming the element and 2 for the explanation. Okay, there's 2 possible answers here with 2 possible different explanations. So let's go through them. Okay, what you can see here is the trends in the first ionization energy across a period. Now, we've got the energy in kilojoules per mole here, and then here we've got period 3. Okay, here we've got the trends in first ionization energy across a period. Here's my crusty little graph. We've got the energy, and then we've got the different elements in period 3. Now, you can see the general trend is going up, but we've got 2 deviations from the trend. One is aluminium, so that's your first possible answer. The reason why, if you look at magnesium, magnesium has 3s2. Aluminium has got 1 electron in the 3p subshell. Make sure you say subshell and not energy level. The energy levels or the quantum levels are like the 3rd energy level. They both have electrons in the 3rd energy level, but aluminium has 1 electron in the 3p subshell. Now, this electron is slightly further from the nucleus and shielded slightly by the 3s pair of electrons, and so therefore it's easier to remove and has an unexpectedly lower ionization energy despite its increasing nuclear charge. So that's our first possible answer. So we have aluminium, nice pink writing. Explanation, has an electron in the 3p subshell, shielded by the 3s2 electrons further from nucleus. Okay, let's look at our second possible answer. Okay, let's look at the second possible answer, and that lies with sulfur. Now, sulfur has the structure here. Again, I've used the shorthand with neon in brackets, 3s2, 3p4. Now, sulfur, you can see here, I've only put 3 electrons so far in the 3p subshell. I'm going to add the 4th electron. What's the problem here? The problem is we get something called spin pair repulsion introduced, and due to this extra repulsion from the spin pair, we find that it has a lower ionization energy than phosphorus, which comes before it, and therefore it's going to be easier to remove. So there's our explanation. Our other possible answer I'm going to do in another color. So let's have a little look here. Something, let's just do it in standard black. Okay, we've got sulfur. This is found obviously in group 6. It has a pair of electrons in 3p orbital. So we have spin pair repulsion, spin pair repulsion. And that's our explanation. Remember, either the answer in pink or black, you could put for all 3 marks. Okay, give an equation, including state symbols, to represent the process that occurs when the 3rd ionization energy of sodium is measured. So we're going to just write this equation out here. Now, 2 electrons have already been removed because we're dealing with a 3rd ionization energy. So we need to write Na2+, and then we're going to go ahead and show the removal of the 3rd electron. So Na2 plus goes to Na3 plus E minus. That's the 3rd electron being removed. Some people will write 3E minus. Don't do that. And remember, essential gaseous state. If you don't put the state symbols, you won't get the marks. There we go. Okay, 1.3. Figure 1 shows the successive ionization energies of a period 3 element X. We've got ionization energy on the y-axis, and on the x we have ionization number. We can see the first 5 electrons are removed with a steady increase in energy, so they're all from the same shell. Whenever you get a huge increase, like you see here between 5 and 6, that means you're breaking into a new energy shell, not orbital, not subshell, but a completely new quantum shell. Okay, so the element has to be phosphorus, as it's the only group 5 element in period 3. And our explanation, there's a large increase in ionization energy with the 6th electron that's removed. And that means we must be removing that electron from a lower energy level. And that's going to be an energy level that's closer to the nucleus. And hence you get less shielding and it feels a stronger nuclear attraction as it's closer to the nucleus. And that's your answer for 3 marks. Yeah, if you can spell nucleus correctly. Okay, let's go through question 2. This is a question about a titration. A student dissolves an unknown mass of sodium hydroxide in water to make 200 centimeter cubed of an aqueous solution. A 25 centimeter cube sample of this sodium hydroxide solution is placed in a conical flask and is titrated with 0.150 mole per decimeter of sulfuric acid. The equation for this reaction is shown. 2 sodium hydroxide aqueous plus sulfuric acid aqueous produces sodium sulfate aqueous and 2 waters liquid. Table 1 shows the results of the titration. 2.1. Calculate the mass of sodium hydroxide used to make the original solution, 5 marks. So what we're looking at here, you should pause the video and have a go, of course. We're looking at how many grams of sodium hydroxide was dissolved in the original 200 centimeter cubed. Let's go. First up, we have the titras. We don't pay attention to the rough titra, but look, we've got the volumes here of the final titras, 1, 2, and 3. So let's find our mean titra, and we need to use concordant results. Hopefully you can work out what the concordant results are. We've got 19.60 and 19.55. The 19.85 is not concordant. Of course, it's not within 0.2 or even 0.1 decimeters. So it's not concordant. So we do 19.60 plus 19.55. We're going to divide that by 2 and find that we have 19.575 or 19.58 if you want to round up centimeters cubed. Okay, so we've got to convert our mean titra into decimeters. Volume in chemistry is always in decimeters. Divide by 1,000, you get 0.019575 decimeter cubed of sulfuric acid. Now we can find the moles if we use the equation moles over concentration times volume. Now we know the concentration because it tells us in the question that the concentration of sulfuric acid is 0.150 mole per decimeter sulfuric acid. Let's times that by the titra, the mean titra, which is the 0.019575, and we'll get our moles of sulfuric acid in the 25 centimeter cube sample. Now we need to find our moles of sodium hydroxide. You can see from the equation that the ratio is 2 to 1. Sulfuric acid's diprotic, so you need 2 sodium hydroxides or 2 hydroxide ions for each acid molecule. So we've got a 1 to 2 ratio, which means we're going to double these moles by 2 and get the moles of sodium hydroxide that neutralize the acid. And we've got 5.87 times 10 to the minus 3. Now, that's our moles of sodium hydroxide in the 25 centimeter cubed sample. So we now need to multiply this up. Remember, we took 25 centimeter cubed from 200. So 200 divided by 25, we need to multiply it by 8 to find out the amount of moles of sodium hydroxide in the original sample, and it's 0.04698 moles of sodium hydroxide in the original sample. So now it's time to work out the mass of sodium hydroxide in the original 200 centimeter cube. Well, we know the moles, and we know that mass over MR times moles will give us the mass. So the MR of sodium hydroxide is 23.1. You can call it 23, plus 16, plus 1 equals 40.1. That's the MR of sodium hydroxide. Let's multiply that by the moles we worked out, 0.04698. And that's going to give us a mass of 1.88 grams. And so that's your answer. Super. And this will score you 5 marks. Okay. 2.2. The student uses a funnel to fill the burette with sulfuric acid before starting the titration. After filling, the student forgets to remove the funnel from the top of the burette. Suggest why this might affect the titer volume recorded. So they've left the funnel in the top of their burette. Check out my GCSE D grade art skills. The problem when they come to read the titer here is they might see the reading as 23 centimeters has been added, but actually 24 was added, but an extra centimeter dripped down from the burette, making it look like only 23 was added. They get an undervaluation of their titer. So the volume added, the volume added is going to be less than what we really added. We get a lower value or an underestimation of our real titer. And the reason being is that some of the sulfuric acid has dripped from the funnel into the burette. Lovely bubbly. Let's move on. Check out the artwork. State one advantage of using a conical flask rather than a beaker for the titration. Well, imagine they used a beaker. What have you got to do when you're carrying out a titration? Remember, you've got to swirl to ensure the reactants are mixed. So as we swirl a beaker, we are more likely to lose some of the contents. If you have a conical flask, and that is an incredible conical flask. There's my D in GCSE art. But if you swirl a conical flask, you're less likely to lose any of your reactants. Okay, so if you're finding the walkthrough helpful, guys, don't forget to smash the like. Make sure you have a go at the questions, then pause the video and then check out the walkthrough. Nice one. All right, let's move on. That's 2 questions down. Let's get into the 3rd question. Okay, question 3.1. Define the relative atomic mass. Average mass of an element compared to 1/12 the mass of an atom of carbon-12. And that's your best definition for the term relative atomic mass, or at least the easiest one to remember. A sample of krypton is ionized using electron impact. The mass spectrum of this sample of krypton has 4 peaks. Here's the data from this spectrum. Calculate the RAM, or the AR, of this sample of krypton. 2 marks. Put your answer to 1 decimal place. We have the MZ ratio, which is equivalent to the mass, and the relative intensity. Remember from GCSE, we called this the relative abundance. So we simply times the AZ of each isotope by its relative intensity, add them all together to get the sum, and divide by the total relative intensity. The big mistake people make here is they sometimes divide by 100, but of course in this case we only need to divide by 43. 1 plus 28 plus 8 plus 6, and that gives us 43. Now, if we calculate this, we should get bada bada bing, bada bada bang, bada bada bing, bang, ba bing bang. 84. Don't forget, they want it to 1 decimal place. 84.1. 4 marks. Let's go. In a time-of-flight mass spectrometer, ions are accelerated to the same kinetic energy, aren't they always? The kinetic energy of an ion is given by the equation Ka equals half mass times velocity squared. So we're going to have to use that equation, where kinetic energy is measured in joules, mass in kilograms, and velocity in meters per second. In a time-of-flight mass spectrometer, each 8 krypton 84 positive ion, is accelerated to a kinetic energy of 4.83 times 10 to the minus 16 joules. And the time of flight is 1.72 times 10 to the minus 5 seconds. Calculate the length in meters of the time of flight tube. So, as we need to know distance, we need to do velocity equals distance over time. We need to rearrange this to find the distance. And so we can write this as distance is equal to velocity times time. Now we have the time, it's 1.72 times 10 to the minus 5. So we need to find the velocity. We're going to use this Ke equals half mass velocity squared. So let's rearrange it. If we times the kinetic energy by 2, gets rid of the half mass, divide by the mass, square root gets rid of the v squared, we equal the velocity. So that is 2 times the kinetic energy, which is 4.83 times 10 to the minus 16. And we need to divide that by the mass, which we don't know at the moment, and we'll square root the answer. So let's check out what the mass is. Well, we've got our krypton 84 positive ion over here, and that tells us that 1 mole is equal to 84 grams, but we need to convert it into kilograms because the Ke equation uses kilograms for mass. So we divide by 1,000, we get 0.084 kg. Now, that's for a whole mole. We want it for 1 ion, so we're going to divide by L, or Avogadro's constant, and that's going to give us our mass, 0.04 over 6.022 times 10 to the 23, and we get 83214.97 meters per second. That's our velocity. So let's multiply that by the time of 1.72 times 10 to the minus 5, and we'll get our final answer of 1.43 meters, and that's the end of the question. Question 4. The question is about enthalpy changes. 4.1. State the meaning of the term enthalpy change as applied to a chemical reaction. This is just a clear definition you have to know. The change in heat or energy, change in heat energy at a constant pressure. Okay, 4.2. A student determines the enthalpy change for a reaction between calcium carbonate and hydrochloric acid. Here's the equation. The student follows this method. Measure out 50 centimeter cubed of 1 mole per decimeter aqueous hydrochloric acid using a measuring cylinder, and pour the acid into a 100 centimeter cube glass beaker. Weigh out 2.50 grams of solid calcium carbonate on a watch glass and tip the solid in the acid. Stir the mixture with a thermometer. Record the maximum temperature reached. The student uses data to determine a value for the enthalpy change. Explain how the experimental method and use of apparatus can be improved to provide more accurate data. Describe how this data from the improved method can be used to determine an accurate value for temperature change. So let's highlight some of the key points and then let's have a go at this question. So what we're really looking at here is what mistakes have they made? Now they measured with a measuring cylinder, but they should have used a pipette. And that's a much more accurate way to measure a volume. You could use a burette, but it's better to use a pipette. Now, what else did they do that was a mistake? We can see that they poured the acid into a 100 centimeter cubed glass beaker. A glass beaker is not a very good insulator, it's more of a conductor. So what they should have used here is a polystyrene cup, which is a better insulator and will reduce the amount of heat lost in the experiment, and you'll get a more accurate measurement for temperature change. Now after that, they weighed out 2.50 grams of solid calcium carbonate on a watch glass and tipped the solid in the acid. Now it's better to reweigh the watch glass after, because you'll probably find some of the solid was left on the watch glass. So reweigh and calculate the amount of solid tipped into the acid. It's also better to use powdered solid. This increases the surface area, make sure all the particles or reactant is exposed for the reaction, and you'll get a more accurate temperature change. Now, how we actually use the data is we want to record several values for the temperature. when it's just the acid before the solid's added, we'll plot that. It's normally a straight line on a graph of time v temperature. Then we're going to add the solid and afterwards make several temperature recordings at regular intervals, like every minute or so. And then what we can do is plot the lines of best fit and extrapolate our line back to the line that represents before the solid is added, and that will help us calculate temperature change. So to find out an accurate temperature change, you record the temperature before adding the solid for a few readings, probably 2 to 4 readings. Then we add the addition of the solid, and that's where our time starts at 0. The addition of the solid, round about there. Next, we start recording the temperature change at regular intervals. We would probably have another couple of these, but we start recording the temperature change at regular intervals. And once we get to our maximum temperature change, we keep recording at regular intervals. Then we plot a line of best fit going up to the maximum temperature change, which is here. And we extrapolate this line back to a point of intersection, which I've not done very well at all. That's very roughly, probably more like up here. Anyway, and this would be our change in temperature. That's our corrected value for the change in temperature. So we're extrapolating back to the point of addition. We're working out that that would be the temperature at 0 at the point of addition by extrapolating our graph back from our maximum temperature. There we go. Okay, 4.3, in a different experiment, 50 centimeter cubed of 0.5 mole per decimeter aqueous hydrochloric acid are reacted with 50 centimeter cubed of 0.5 mole per decimeter aqueous sodium hydroxide. You can see from the equation that it's a 1-to-1 reaction. We have an enthalpy change here of minus 57.1 kilojoule per mole. The initial temperature of each solution is 18.5 degrees. Calculate the maximum final temperature of the reaction mixture. Assume the specific heat capacity of the reaction mixture, C equals 4.18 joules. Assume the density of the reaction mixture is 1 gram per centimeter cubed. So let's get down to it. Pause the video, have a go at this, and then we'll get into it. Stick around.
I'm gonna have to science the shit out of this.
Okay, we're looking to find Q equals MC delta T. Now, in order to find the maximum final temperature, we need to find delta T. So let's rearrange Q to find delta T. And we're going to need to do Q, my gosh, that's a crazy Q, divided by MC. MC, and that's going to equal the change in temperature. Okay, but first of all, we need Q basically, which would be beautiful. Let's find Q first. So to find Q, we take this enthalpy change and we need to turn this back into joules. So we need to get rid of the per mole and we need to get rid of the kilojoules. To get rid of the kilojoules and turn it just into joules, we times by 1,000, and then we will have joules per mole. To get rid of the moles, we need to times by the number of moles. Now, in order to calculate the number of moles, we're going to do concentration times volume. My gosh, that is a strange looking N. Okay, so the concentration of both of these, well, we've got the volume of 50 centimeters cubed and the concentration of 0.5 mole per decimeter. Doesn't matter which one we use. So we're going to do 0.05. That is the volume. Once I've divided by 1,000, those 50 centimeters, and then times that by the concentration, which is 0.50, and that's the concentration. And that's going to give me 0.025 moles of acid or of the alkali sodium hydroxide. As it's a 1-to-1, it doesn't matter which one we use. Also, we have the identical amount of moles of each. Now, in a situation where you have excess amount of one of the reactants, you're going to use the limiting reactant as your number of moles. So just remember that. In many of the questions, they'll give you an equal amount of moles of both reactants to simplify it a little. So we have the number of moles. We need to go minus 57.1 times 1,000 times 0.025. Now let's whack that in the calculator and see what Q is. And we get 1,427.5 joules, and that is Q. Now we need to do 1,427, oh my gosh, I'm losing the wheel here, 0.5 joules, and we need to divide that by the mass. How do we know what the mass is? Well, we have 100 centimeters in our solution, and we are told that it's 1 gram per centimeter. So our mass is 100 grams, and we're going to times that by C, which is the specific heat capacity, and that is going to give us our temperature change. Now, our temperature change is going to equal 3.4 degrees. Add that to the original temperature, 18.5 plus 3.4. Whoa, that's messy writing. And we're going to get 21.9 degrees. And that is the final answer. And that's our temperature change. Hope that was clear enough. If it was clear as mud, leave a comment. If not, leave a comment too. Hit percentage uncertainty is 0.1 divided by 50 times 100. And if we do that, we get 0.2. And that would be our percentage of uncertainty in the experiment. So what happens if we double the temperature change? We don't have to change any of the equipment. We just say, hey, let's double the temperature change. Well, our uncertainty, 0.1, stays the same. But the change in the temperature, we've managed to double. And of course, if we do that, 0.1 over 100 times 100, we're going to get 0.1%. Look what we've done. By doubling the temperature change, we have halved the percentage uncertainty. So what could we do in this experiment here that we've been carrying out to increase the temperature change? Because that will lower the percentage uncertainty. Now, it won't change the uncertainty in the measurement because that will be the same. We're using the same apparatus. But by having a larger temperature change, we get a lower percentage. And of course, to do that, we need to increase the concentration of the reactants. And there we go. We just need to increase the concentration of the reactants. But okay, question 5. This question is about group 2 elements and their compounds. 5.1, explain why the melting point of magnesium is higher than the melting point of sodium. So have a go at the question and then pause the video, as you do, and then I'll go through the answers. All right, here we go. Let's go through it. Well, if we look at sodium, okay, sodium is the first element in the period, so that's period 3. And then we have magnesium. Now, as you go across the period, the elements get smaller due to increasing nuclear charge. Sodium has 11 protons. Magnesium has got 12 protons. So as you're looking at it, magnesium's getting smaller, but has a bigger nuclear charge. Now, of course, magnesium ions have a 2+ charge and sodium ions a 1+ charge. So what essentially we've got is a higher charge over a smaller ion with magnesium. So what we can say there is magnesium has a higher charge density. And this means that its nuclear charge is spread over a smaller ion, and it's got a 2+ charge compared to a 1+ charge. So we could also add Mg is 2+, whereas Na is just plus. Now we're going to combine that with the fact that how many delocalized electrons does each magnesium ion release? Well, magnesium is 2+, so it has 2 delocalized electrons attracted to that 2+, and sodium is 1+. So where are we going to get the stronger attraction? Well, Mg has double the delocalized electrons compared to Na. So twice as many delocalized electrons. All of this is going to result in a stronger force of electrostatic attraction between the magnesium and the electrons than there is in the sodium. So, or stronger metallic bonds. So we can say stronger electrostatic force of attraction between Mg ions and delocalized electrons. Or we could also say stronger metallic bonds in Mg. Okay, let's look at this question, 05.2. Give an equation to show how magnesium is used as the reducing agent in the extraction of titanium. Explain in terms of oxidation states why magnesium is the reducing agent. Okay, first of all, they want us to write the equation and then an explanation. So in order to write the equation, we need to know that magnesium, which is more reactive than titanium, is going to displace titanium like so. We're going to get titanium has a +4 oxidation state when it's an ion generally, so we're going to get magnesium chloride. Of course, magnesium is +2, it's in group 2, and we just need to balance this. So you should be good at balancing by now. That means I'm going to need 2 magnesiums because I'm going to need 2 of these to make the 4 chlorides. And there we go, balanced super duperly. Lovely. Right, explanation. Let's check this out. Let me pick a different color pen. Boom. Okay, let's check out what's happening to magnesium, guys. Let's have a little look at its oxidation state. In its elemental form, what's its oxidation state? It's 0. Once it's in its ionic form, magnesium has a +2 oxidation state. So what can we say about magnesium? Magnesium loses 2 electrons. And what does that mean? It has been oxidized. You should know oil rig, magnesium's been oxidized. Let's check out the titanium, okay? Whip in a different color. I've not left myself any room. So if we go with titanium, titanium ends up as 0 oxidation state here in its pure elemental form. And over here, you can see it's attached to 4 chloride ions, which have a -1 oxidation state. Titanium has a +4 oxidation state. So titanium has gained 4 electrons and been reduced. You remember oil rig, reduction is gain of electrons. So titanium has gained 4 electrons and has been reduced. Voila, there are the answers. (5.3) State what is observed when dilute aqueous sodium hydroxide is added to separate solutions of magnesium chloride and barium chloride. Okay, we're going to get a white precipitate, and we're going to get no change. Question 6. Question is about the shapes of molecules and ions. Draw the shape of NCl3 and NCl4 plus ion. Include any lone pairs of electrons that influence the shape. Name the shape of the NCl3. State and explain the bond angle in NCl4 plus. Okay, let's go. Shape of NCl3. I'm just going to go through all the bits. Obviously, let's get that shape of NCl3 down. So how do I work it out? Well, I go nitrogen. What group's it in? You should know by now off by heart. Group 5 for nitrogen. Okay, how many bonds are there? Check it out. There's 3 bonds. So we take the 5 electrons around the central atom, which I find by its group number, add them to the bonds, and we get a total of 8 electrons around the central atom. We divide it by 2 to find the number of pairs of electrons, and that tells us we have 4 pairs of electrons. Lovely. Okay, how many lone pairs of electrons do we have? Take the 4 pairs and minus the electron pairs or minus the number of bonds, because that's the pairs of electrons in bonds. So 4 minus 3 equals 1 lone pair. So let's draw it out. We know it's got 4 pairs. Do you remember the 3 possible shapes for 4 pairs? And then if you look, you should know these off by heart. You can get the old, I don't know, I'm writing ammonia. It's basically the same shape as ammonia. If you know your shape of ammonia from all your revision, you probably do. Okay, you need a solid triangle coming out and one going in. Okay, lovely jubbly. Now, just out of pure interest, it's not part of the question. That's going to get you the marks. The name of this shape is pyramidal, and you should know your bond angles. So I believe it's 107. Lovely jubbly. Okay, you don't have to put a cloud around the lone pair. Some people like to do that, but there you go. Let's check out the next one. So again, nitrogen, group 5. This time, how many bonds? 4 bonds. Now, going back to the group 5, we have an issue. There is a positive charge. This means we lose one of the electrons. So essentially, because of the positive charge, instead of having 5 electrons, we've only got 4 electrons. So we go 4 plus 4 equals 8. Divide by 2. Surprise, surprise. We have 4 pairs of electrons. We take the 4 pairs of electrons, we minus the number of bonds, bonded pairs. We have 0 lone pairs of electrons. When you have 4 pairs and 0 lone pairs, you're going to be tetrahedral. So we're going to go Cl. Oh my gosh, check that out. Cl. Okay, this is the ugliest tetrahedral shape ever drawn by humans. And then you need to put brackets, and you need to put the charge outside the brackets. And we should put, it's 109.5. Now, important with this, I've left myself no room for writing because I'm a bit of an idiot, but it actually says state and explain the bond angle in NCl4+. Didn't ask me to draw it all out, so I'm only really getting a mark for the 109.5 bond angle. Why does it have a 109.5 bond angle? Well, we have 4 pairs of electrons with equal repulsion. So because you've got equal repulsion and they repel as far apart as possible. So equal repulsion, repel as far apart as possible. 4 pairs of electrons, equal repulsion. So we get a bond angle of 109.5. Lovely jubbly. Question 7. This question is about the group 7 elements and their compounds. Chlorine is used to treat water, even though it is toxic to humans. Ooh. Give one reason why water is treated with chlorine. I bet you've all been in the swimming pool without your goggles and your eyes sting. That's the chlorine. Explain why chlorine is added to water, even though it is toxic. Give an equation for the reaction of chlorine with cold water. So the reason we stick chlorine in water is basically very simple. It kills bacteria. It sterilizes the water, or disinfects the water, kills microbes, but essentially kills bacteria is my answer. But there's plenty of other answers you could put. Now, the health benefits outweigh the risks. So the risks of cholera or other waterborne diseases spreading in a swimming pool or from drinking water from your tap far outweigh the risks that are related to chlorinating your water. Okay, and we can see that in societies that don't chlorinate their water and societies that do chlorinate their water for whatever reasons, the health benefits outweigh the risks. Okay, let's get down to the equation. So we have chlorine, oh, red, nice choice of colors, not, plus H2O in a reversible reaction. is going to make hydrogen chloride and plus hydrogen chlorate. There we go. Lovely jubbly. Okay, next question. Solid sodium iodide reacts with concentrated sulfuric acid to form iodine and sulfur in a redox reaction. Give a half equation to show the conversion of iodide ions to iodine. Give a half equation to show the conversion of sulfuric acid to sulfur. Give an overall equation for this redox reaction. Identify one other sulfur-containing reduction product formed when solid sodium iodide reacts with concentrated sulfuric acid. So let's start. 4 marks. Nice. Half equation for the conversion of iodide ions to iodine. So we want to write our iodide ions here, and we're converting those to iodine. Now, you should remember by now, you're doing A-level, iodine is diatomic, so we need I2. That means I'm going to need 2 iodide ions, and of course, they're going to release 2 electrons. I like to put a little minus next to my electron, but it's not required. Half equation for the conversion of sulfuric acid to sulfur. So we want to start with sulfuric acid, like this, H2SO4. You should know that off by heart. If you don't know that off by heart, you've got issues, sort them out. And it tells us that that's going to make sulfur. So that's our starting position. But what else? Well, you can see here I've got hydrogen on the left and oxygen. So I'm going to have to make water as well. Now, I'm going to need to balance this all up. I've got 4 oxygens. So how many waters do I need? Well, if I've got 4 oxygens in the sulfate group and the sulfuric acid, I need 4 H2Os. And that means I need another 6 hydrogens over here. So I can add 6 hydrogen ions. Now that leaves me with an issue because I have a positive charge on the left-hand side. Well, I can cancel that out by adding myself 6 electrons. There you go. There's the half equation. Right, what's the overall equation? So what we do now with the overall equation is we look at the number of electrons in each of the half equations. So I have 6 electrons here and only 2 electrons here. So in order for me to balance these 2 half equations, I'm going to need to multiply this equation by 3. And if I multiply all of the subjects in that equation by 3 and combine the 2 equations together, cancel out my electrons, and I've got the full equation. So it's going to look something like this when you get down to it. So the overall equation is 6H plus we've tripled the amount of iodide ions we had in the half equation above. So we've now got 6 iodide ions plus 1 molecule of H2SO4. We won't need to put the electrons down because there will be 6 electrons on both sides of the equation, so we're cancelling those out. However, we also tripled our iodine molecules, so we have 3 of those. We have our sulfur and our 4 waters. So it's literally a case of cancel out the electrons because they are equal on each side. And there you go. That's your full equation, combining those 2. What other sulfur-containing reduction product is formed? So identify over here, identify one other sulfur-containing reduction product formed when solid sodium iodide reacts with concentrated sulfuric acid. And of course, iodide is the best reducing agent out of the halides we study in AQA. So it gets quite a few extra products formed, and we can have sulfur dioxide or hydrogen sulfide. And either one of those will score you the marks. Let's move on. A student completes an experiment to determine the percentage by mass of sodium chloride in a mixture of sodium chloride and sodium iodide. The student uses this method. 600 micrograms of the mixture are dissolved. Bomber clots. A student completes an experiment to determine the percentage by mass of sodium chloride in a mixture of sodium chloride and sodium iodide. The student uses this method. 600 milligrams of the mixture are dissolved in water to form a solution. An excess of aqueous silver nitrate is added to the solution. This forms a precipitate containing silver chloride and silver iodide. Excess dilute ammonia solution is then added to the precipitate. The silver chloride dissolves. The silver iodide is filtered off from the solution and is then washed and dried. The mass of the silver iodide is 315 milligrams. Silver nitrate is added to the solution. Suggests why an excess is added. And this is basically to ensure that all the iodide and chloride ions react and precipitate out of the solution. Lovely jubbly. Now, the next question. Calculate the amount of moles of silver iodide obtained. The MR of silver iodide equals 234.8. Thank you very much. So what we need to do here, nice and simple, is calculate the moles of silver iodide obtained. Well, that's quite easy. We've got 315 mg. Of course, moles use grams as the mass, so we need to divide by 1,000, and this will leave us with 0.315, check out the writing, grams. We're going to divide that by the MR of the silver iodide, kindly given by AQA there, but it is only 1 mark. They're not that generous. So 0.315 divided by 234.8, and we get a lovely grand sum of 0.00134. Or, if you like, you could write this as 1.34 times 10 to the minus 3. So it all depends what you like. And that's the number of moles. I like to write an N, but there we go. 7.5, calculate using your answer to question 0.74, the mass in grams of sodium iodide in the mixture. So we want to do, we know that we have 1.34 times 10 to the minus 3 moles, and that is going to be our moles of sodium iodide. Got to use our answer from the last question, as it tells us. And then we want to multiply that by the MR, which they have kindly given us over here. So multiply that. Moles times MR equals mass, and we're going to find that that gives us 0.201 grams of sodium iodide. Lovely jubbly. Now, calculate using your answer to 7.5 the percentage by mass of sodium chloride in the mixture. So we know we had 600 milligrams. So we're going to take away 201, which is going to equal 399. You might say, where'd you get the 201 from? Well, that is the 0.201 grams of sodium iodide that I've removed. And now that's going to leave me with 399 milligrams of the sodium chloride. So now I know how much sodium chloride I've got. I can do 399 divided by the total mass of 600 times 100, and that's going to give me roughly 66.5%. Wunderbar. Oh my gosh, this question is about a volatile liquid A. This is question 8. This question is about volatile liquid A. 8.1, a student does an experiment to determine the relative molecular mass, the MR, of liquid A using the apparatus shown in figure 0.2 down here. The student injects a sample of A into a gas syringe into an oven. At the temperature of the oven, liquid A vaporizes. Calculate the MR of A. Give your answer to 3 significant figures. Always remember that, guys. So many people lose a mark there. We have the gas constant, 8.31, joule K mole to the -1. Listen, we know when we've got that, we're looking at the ideal gas equation. They've been talking about gases, gas syringe, vaporize, and then we look at the data they've given us. We've got pressure, we've got the ideal gas equation. So you should remember that PV equals nRT. Now, they want us to calculate MR. That is the focus. In order to calculate the MR, I need to find moles. So I need to rearrange this equation to make moles the subject. So we're looking at PV over RT. You're going to divide PV by RT, and that's going to leave you with moles on its own. And that's what we need to get down to. Now it's all about converting these units up here. The grams we can leave till we have the moles, and then we whack that in to find the MR. But let's get down to the rest of it. So pressure, what have we got? 100 kilopascals. Now, you must learn this off by heart, of course. All these situations, practice, practice, practice. 100,000. We need to use pascals in this question for pressure, not kilopascals. Now, we're going to multiply that by the volume. The volume is in meters cubed. What is the volume? 0 before, 178 after. So I need to do 178, and I want to divide that, we're putting this into meters cubed, by 1 times 10 to the 6. Okay, why do I want to do that? Well, we need to put it into meters cubed, and there are 1,000,000 centimeters cubed in 1 meter cubed. So I'm dividing by 1,000,000. Now, the next little thing that we've got to do over here is come up with the temperature of the oven is 120. We need to convert that into Kelvin. So 120 in Kelvin, 273 plus 100 is 373 plus 20 is 393. Sorry, it took a while for my brain to work there. And of course, what is R? Doing it in a backwards order. What is R? R is 8.31. Whack this all into the calculator. And we get N, which is our moles, is equal to 5.45 times 10 to the -3, or 0.00545. Now, that's our moles. How do we now need to rearrange this equation, which I'm whacking over here? Moles over mass. Oh, gosh. I do not know what I am doing. Right, let's do this. That is the most bent diagram ever. Okay, mass, MR, and moles. Good to remember that. Mass over moles equals MR. So we want to find the mass. We have the mass before injection, the mass after injection. Let's whack that in. So we've got 11 point, we can just do 11.295 in your calculator, subtract 10.835, smash that over the top of the MR, the moles, which was 5.45 times 10 to the -3. Oh my gosh. And that is going to give us our lovely jubbly MR, roughly 84.4. Remember 3 significant figures, and that is our MR. 5 marks. Boom! Or 4 marks. Yeah. Okay. The student noticed that some of the liquid injected into the gas syringe did not vaporize. Explain the effect this had on the MR. Well, basically, you're going to have lower volume, right? Which is going to give you lower moles. Because you've got lower moles, you're going to do mass divided by moles. As the N is smaller, we get a greater MR than expected. Nice. So you get a smaller volume because less is vaporized. So smaller volume, that's your P times V, is smaller, which means that when we do PV over RT, we get a smaller N, which is the moles. And then when we do mass over N, we get a greater answer because the N at the bottom is smaller in that equation. So our MR is greater than expected. And that's a very common question on these. So each reading on the balance used to record the mass of the fine needle syringe and contents had an uncertainty of plus 0.001 grams. Calculate the percentage uncertainty in the mass of the liquid A injected in this experiment. So it says each reading on the balance, and we've got two readings on the balance. So we need to do 2 times 0.001. Percentage uncertainty is where you divide the uncertainty, the total uncertainty, so we're doubling that because there's two readings, over our reading. So what was our reading? Our reading was 0.460, and you get that from doing the final mass, take away the initial mass, and there we go, times 100. Our percentage uncertainty is 0.35%. Lovely jubbly. Okay, time for the multiple choice questions. Let's go. Question 9. Which atom has the smallest number of neutrons? So we've got A, which is hydrogen 3, B, helium 4, C, helium 5, or D, lithium 4. So what we want to do here is find out their atomic number and then subtract the mass number or the atomic number from the mass number, and that will give us the number of neutrons. So let's write the atomic numbers down here, easily found in your periodic table. Subtract from the mass number, and we're going to find that lithium 4 would only have 1 neutron, so the answer is D. Question 10. Which species contains bonds that have different polarities? So let's have a little look here. Well, we've got NH4+, CCl4, CH3Cl, and H3O. The answer obviously here is going to be C. What's the reason? Well, it's the only one which has different bonds, so of course they might have different polarities. The chlorine is delta negative, the carbon's delta positive. We know the hydrogen's delta positive as well, and the carbon, but they're not going to be as big a difference in electronegativity as between carbon and chlorine. Let's look at this next one. Which compound has hydrogen bonding? Question 11. So really, you've got to remember there are only 3 elements that give us hydrogen bonding. When oxygen is bonded to hydrogen, or fluorine is bonded to hydrogen, or nitrogen is bonded to hydrogen, you will only get hydrogen bonding if you see this bond in a molecule. And the only molecule here with one of those is ammonia, NH3. So the answer is B. Question 12. Which reaction has an enthalpy change equal to the standard enthalpy of formation of lithium fluoride? Essentially, this is asking you for the equation for the formation of lithium fluoride. Now, if you know your definition off by heart, which you should do, you'll know that it's the formation of the compound from the elements in their physical state at room temperature and pressure under standard conditions. So lithium would be solid, fluorine would be a gas, and lithium fluoride would be solid. So the answer is D. Now the next one is the nitrate ions, NO3-. They can be reduced by an acidic solution to nitrogen monoxide, NO. How many electrons are gained when each NO2- ion is reduced? We remember that reduction is gain, oil rig, reduction is gain of electrons. So when the NO2 ion is reduced and gains electrons, how many does it gain? Well, let's look at the oxidation states. In the nitrate ion, the oxidation state of nitrogen is +3. If we look at the NO molecule, we'll see that oxygen's always -2 unless it's with fluorine. That means that nitrogen must be +2. There's no overall charge, it's a neutral compound. So what's happened between the nitrogen in both of these molecules? Well, we can see that it was +3, but then it gained an electron to become +2, which means it's been reduced. How many electrons did it gain? It gained 1 electron. So the answer is A. Let's go on to the next question. Question 17. Right. Question 14. Gosh, I can't really add up. Which is the electronic configuration of an atom with only two unpaired electrons? So we're looking for two electrons on their row in their orbitals. So if we draw out the subshell for, well, we draw out the 2p orbitals, we'll see here 2p3. How many single electrons are there? There's three unpaired electrons. If we draw out for B 2p4, you're going to find that you have one filled orbital and two unpaired electrons. So the answer is definitely going to be B. We can see that. But let's go through the others just so you get the idea. So for C, we draw out 3p5. This has only one unpaired electron. And then for the final one, we have 3d5. Now there are five orbitals and each one has one electron. So that's five unpaired electrons. So the answer is definitely B. Question 15, which represents the correct order of increasing radius of the ions? Now we're looking here at period 2. Generally, they decrease across a period, but we're looking at ions here. Now, negative ions are going to be larger than positive ions because negative ions, you get that extra repulsion between the electrons. So really, when you're looking at B and C, you can see beryllium has a greater positive charge than lithium, so it's going to be smaller. Lithium has less positive charge. And then fluorine and oxygen, we can see we've got a fluorine minus ion and an oxygen 2 minus ion, so they are going to be larger. The greater the negative charge, the greater the repulsion, the bigger the radius of the ion. Okay, let's go into look at, so the answer is C. 16. Which compound contains a coordinate bond? You have to remember the definition of a coordinate bond. It's where a pair of electrons in the covalent bond are donated from one species or one atom. And we're really looking at ammonium chloride for that one. The answer is D. You can actually draw all of these out to see that it contains a coordinate bond, but you should know your ammonium ion, your NH4 plus, contains a coordinate bond. So which property increases down group 7? Nice, easy question. I'd have a quick read of them and then see if you get a nice, easy answer. And you can see here, B, the boiling point. Well, that one's nice and easy. Fluorine's a gas, chlorine's a gas, bromine is a liquid at room temperature, and iodine is solid. So quite clearly, the boiling point is increasing down the group. Which of these elements has the highest melting point? So very similar to this, we're really looking at argon. Let's check it out. Let's check out their state at room temperature. You might know these off by heart. Argon's a gas, chlorine's a gas, silicon and sulfur are solid. So the highest melting point is either silicon or sulfur. So we really just want to look at the mass number or the atomic number, because the larger the atomic number and mass number, you're going to get larger intermolecular forces. So yeah, the answer here is going to be sulfur. D. Let's move on. So we're into the last few questions now. We're up to question 19 on the multiple choice. So let's check it out. Which statement is not always correct for a reaction at equilibrium? So we've got a little reactants, reversible symbol products, which you always get in a closed system at equilibrium. The concentrations of the reactants and products are equal. The equilibrium can be achieved starting from the reactants or starting from the products. The rate of reaction for reaction is equal to the rate of the reverse. Well, if we go from the bottom up, just for the sake of it, so I can explain it, you can see these are all true. You can go either way. So you could start with the products and get the reactants, or the reactants and get the products. The only one that's not true is that at equilibrium, you won't always have the same amount of product and reactant. In fact, very rarely will you have the same amount of reactant and product. The concentrations of them will not be equal under normal circumstances. Well, rarely will they be equal. The forward and backward reaction, the rate of the reaction will be equal, which is D. Okay, let's move on. Let's look at question 20. Two reactions of iron with oxygen are shown. We've got solid iron plus oxygen gas makes iron oxide. iron 2 oxide. Then we've got iron plus oxygen makes iron 3 oxide. And we have the enthalpy changes. And then it says, what would be the enthalpy change for the reaction below? We've got iron 2 oxide being added to oxygen to make iron 3 oxide. Well, we can combine these two reactions above. And how we do this, we start with iron oxide and we're going from right to left. So we're looking at the enthalpy changes minus 272, but there are 2 moles of it. So we should really double that to make minus 544 because there's 2 moles of it. And we're going in this direction. Now, because we're going in the backwards direction, we want to change the sign and make it positive because we're going in the opposite direction from the enthalpy change we're given. Now, once we've created the iron and the oxygen from the iron 2 oxide, it's going to be rearranged and formed into iron 3 oxide. And when we do that, we get an enthalpy change of minus 822 kilojoules per mole. So now all we need to do is double the first reaction because there are 2 moles of the iron 2 oxide breaking down into the elements. So we're going to double that. 2 times minus 272, we're going to get minus 544. But we must remember that's plus 544 and minus 822 because we're going in the correct direction with the bottom reaction and the opposite direction with the top reaction. And when you do add those together, plus 544 and minus 822, you get an answer of minus 278. If my calculations are correct, doing that all in my head, I should really use my calculator. Okay, and that's the answer for 20. So you're combining those two reactions to make the one reaction below. You're doubling the top number, reversing the symbol, and then you're using the enthalpy change minus 822 as you're going in that correct direction with the bottom reaction. All right, let's move on to the final questions in this exam paper. So we're looking now at question 21 and 22. 21. Which compound contains chlorine in an oxidation state of +1? Quite simple. Just practice writing out your oxidation states. So for D, chlorine is in a -1 oxidation state. You can see carbon is +4. It's in group 4. For C, fluorine is going to be -1 because it's more electronegative than chlorine, which means that the chlorine must be +3 as there are 3 -1 fluorines. Let's look at B. Well, we know that oxygen is always -2 unless it is bonded to fluorine or in a compound with fluorine, then it could become positive. So as I go to oxygen as my second most electronegative element as -2, we know there's a total of -6. We know that potassium must be +1 as it's a group 1 element, so chlorine must be +5. Now if we look at A, oxygen is -2. There are 2 chlorines, each one must be +1 to make +2 and create the neutral compound. So the answer is A. 22. Which equation shows a redox reaction that does not occur? Well, we can get into the whole reduction and oxidation and the transfer of electrons, but essentially you should remember from GCSE that the halogens get less reactive as we go down the group, and you studied the displacement reactions of the halogens at GCSE. So which of these reactions would not occur? We can see for D, iodine is the least reactive of the first 4 halogens, so it definitely couldn't displace bromide from potassium bromide to form bromine. So the answer is D. That reaction could not occur. Okay, moving on to the final question, question 23. Which molecule has a permanent dipole? Well, what you'd really have to do for this, I'm going to whiz through it, but what you really have to do for this is draw out each molecule, look at the dipoles. So we can see here that carbon is electropositive, fluorine is electronegative, so you will have a dipole. Problem is it's a symmetrical molecule. So they're all going to cancel out. Same with carbon dioxide. If we drew carbon dioxide out, carbon dioxide is a linear molecule, which means that although oxygen is electronegative and carbon electropositive, the dipoles will cancel out. So the only one with a permanent dipole is D. And that's because when you draw it out, it looks a little bit like water. And so therefore it's not symmetrical and the dipoles don't cancel. So the dipole is permanent.
You're still here? It's over.